What this video is about is performing the paired t-test within the JUMP framework. Now I've got a data set here, it's a little one, it's called taste, and the origin of this data set is a taste test. 16 individuals, you can see them, 1 through 16, have been given 2 T's to taste. And the first T goes in the first column and the second T in the second column. Now, the rating scale for this was a little bit strange. It was a 1 through 7 scale, and the lower the number, the more the tea was liked. So we can have a look at these 2 T's in terms of the average rating, and so let's do that quickly just through the distribution dialog. And having a look at this, you can see that the average rating for the ones was a 3.5, and the average rating for the second T was a 4.3, and low is good here, so 1 is being preferred over 2, at least in terms of the sample means. But our question, as usual, is whether or not the difference we have observed is statistically significant or is attributable to chance variation. Now, as usual, we are anticipating that we have a random sample from some underlying population. And in that context, we're testing whether or not the difference in population means is equal to 0 or not equal to 0. So we're going to do a two-sided alternative, because we're not going into this with a particular T as having some assumed preference over the other one. So we're not thinking of a one-sided alternative. That's what I'm saying here. So in order to do this paired t-test, we need to create the column of differences. So the way I'm going to do that is double-click there at the end of the spreadsheet. And if I click again, I can give the column a sensible title. Let's call it diff. And I am going to now use the formula dialog. And I'm going to do taste2 minus taste1. And have a look at that. So differencing here made sense because each individual tried out the 2 T's. And so the first row, the 3 and the 4, are 2 observations on the same experimental unit. And this first individual gave taste 1, T1, a lower score than 2. And remember, low is good here. The difference here is positive because I did 2 minus 1, and the positive number there is indicating that this individual preferred the first T. Second individual preferred the first T even more. They gave it to 2 in terms of a difference. You see the minus 1 there? That's because this individual, person 3, actually preferred the second T over the first. And if we scan down here, here's a row where the difference is 0, and that means that the individual gave the same rating to both T's. So this is the indifference value, 0. So what we're now going to do is take that column of differences and apply a one-sample t-test to it. And when we do a one-sample t-test on the column of differences, that is the paired t-test in action. So again, the absolutely critical thing here is that this differencing operation makes sense, and it does here because we've got 2 observations on each person, and that difference value reveals the preference of each individual for the 2 T's. So let's now go ahead and analyze that column of differences. So that's a single column, so we do distribution, and we're going to look at those differences now, and here they are. And if we have a look at the average of the column of differences, it's 0.81. It's a positive number, which indicates that the first T is being preferred on average over the second T. There's a standard error of the mean there, 0.33, and as usual, the 95% confidence interval. And the thing to note here is that this confidence interval does not contain 0. It's all positive numbers, and so we can conclude from a statistical perspective that the first T is preferred over the second one. There's statistical significance there, and that was a 95% confidence interval. If we want to do a hypothesis test and get a p-value, we right-click on the title bar, go to test mean, and now the appropriate null hypothesis is the one that's gone in by default there, 0, because if the column of differences is coming from a population with mean 0, then the averages of the 2 underlying columns of the population means of the 2 underlying columns is the same. Now, we're always given the option to put in a true standard deviation, with the standard deviation of the differences if we had it, but of course we don't. If we don't know the mean, we're very unlikely to know the standard deviation, so we just leave that one blank. And then it's just a question of clicking on OK. Now if we have a look on the screen here and see the output of the paired t-test, we go under the test mean part of the output, the hypothesized value, and you have to remember that this was for the difference, it's 0. Here's the estimated difference in the sample means. The mean of the column of difference is about 0.8. And if we go down here to the t-test, we can see that what we have observed in terms of the average of the differences is a 2.45 standard error event. You ask yourself, is that common or rare? Well, it's by our usual definition rare because it's greater than the cutoff 2. Recall that the cutoff of plus or minus 2 on the t-statistic will give you a test with a type 1 error rate of 5%. Equivalently, in terms of getting a conclusion, we can look at the p-value there, and I'm looking at the two-sided p-value because I was doing a two-sided alternative hypothesis, and it's 0.0271, which is less than the classic 0.05. So we have evidence to reject the null hypothesis. In terms of visualizing that two-sided p-value, you can go down to the distribution, the test statistic under the null, centered around 0. Here's the observed value of the difference in means, the little red tick mark there at let's find the difference, 0.8125. Yes, that's about at 0.81. And the p-value, the two-sided p-value, is comprised of the tail area to the right of it and the symmetric tail area to the left. The sum of those two dark blue areas is going to equal that p-value there, the 0.0271. And we would view that as a small p-value, less than 0.05, so evidence to reject the null. So just a couple of other things to always bear in mind when we've done one of these hypothesis tests. We have identified statistical significance. It doesn't mean that it's practically important, and it would be up to the experts in this field to decide whether or not the observed difference in means, the 0.8, is a meaningful difference between the ratings of the two t's. Final thing, why is it that the paired t-test is working for us here? In what sense is it appropriate to do the paired t-test? Well, we have the two observations on each experimental unit, but we can also plot those against one another. Let's plot taste 1 against taste 2 and just have a look at that distribution. And you can see there is some correlation there, and so I'll quickly find what that correlation is by grabbing the density ellipse, opening up the correlation. And the correlation is 0.6, a positive correlation between these two observations. And what that is really telling you is that individuals, each point here is now an individual. Here's a person who gave the t's a 6 and a 6. They really didn't like either of them. And here's a person down here who gave the t's a 2 and a 1. They loved t. So there's variation in the ratings. Not just because people like the t's differently, but because some people are t lovers and some people don't like t at all. Some people give them both high ratings and others give them both low ratings. But by doing the differencing, we're able to identify preference. And that's the meaning of the differencing in this particular context. So it's all about a positive correlation between the two observations, which is the attribute of the data that we're taking advantage of by saying it makes a lot of sense here to do the paired t-test. So there's the paired t-test in JUMP. And very quickly before I finish this, there is an alternative way of obtaining the paired t-test in JUMP. I showed it to you by manually creating the column of differences, and that is a fine thing to do. But you can do a little bit quicker. If you go to Analyze and then Matched Pairs, here's an alternative dialog where you can put in the two t's, taste 1 and taste 2, the two columns, the paired response as it says. Click on OK. You get some interesting output, but if we quickly go down here and have a look at the summaries, taste 2 has got a mean of 4.3, taste 1 has got a mean of 3.5. There's the difference again of means 0.81. Here's the 95% confidence interval 0.1 to 1.5, and there's the p-value 0.0271. This is identical to the output that we got when we did it by hand by creating the column of differences. So JUMP's paired t-test dialog simply does the column of differences on your behalf. And it gives you this sort of interesting looking graphic here. It's got a little bit of information in that can be quite useful. If you look at the horizontal axis, you get the mean of taste 2 plus taste 1 over 2. So that's the average rating. So in the horizontal axis, you've basically got how much you like tea. And in the vertical axis, we've got taste 2 minus taste 1. That's revealing the preference. And so when we plot preference against how much you like tea, you have the potential to identify whether there's some systematic change in preference as a function of how much you like tea. So in summary, this is a diagnostic plot. In this particular case, I don't see any strong relationship here, and so there's no evidence against the most straightforward view that the preference is the same over how much you like tea. Tea lovers down here and tea haters at the other end. So with only 16 data points, it's really, one shouldn't read too much into one of these diagnostic plots, but with more data points, it could be quite useful. So that's a quick way of doing the paired t-test in JUMP. It's not necessary to do it like that. You can do it either way. You'll get the same result. That completes the paired t-test discussion.